Thank you for joining me today. This video is going to be the first part of a series I call a practical guide to CMake and native project management. So we're going to cover just the basics of CMake and get comfortable with it. So for those of you who aren't familiar, CMake is a build system generator. It's not itself a build system the way that Make or Ninja or an IDE's project might be a build system. Rather, it generates those files. So I want to get started just immediately with an example of what this looks like. So I'm working in a Linux environment. The steps will look basically the same in Windows. Um, and I'm just going to start by making a really basic CMake project. So let's start. So all CMake projects have a CMake lists.txt file. The top level CMake lists.txt is where your project begins. So the first thing that your top level CMake file should start with is this CMake minimum required command. So CMake is, it's been around for a while. It's a stable piece of software though. They rarely do breaking changes, but when they do, they allow you to set what they call policies. We'll take a look at this a bit more later, but the idea is you can make CMake behave the way it did in a particular version. So here we can say CMake minimum required version. We'll say 3.10 for now, and even if we're on version 3.11, 3.12, 3.13, this will make CMake behave as if it were version 3.10. So this is really handy to make sure that your projects are always compatible going forward. Again, we'll look later at how to configure policies individually. Generally, it's not something that needs to be worried about. So this is definitely how your top level CMake should begin. There's a decent argument for saying this is how every CMake lists TXT should begin, especially for modules, which we'll go over later. But just know that this is to make behavior consistent across CMake upgrades. Next command we're going to use is the project command. So this is analogous to a project in an IDE. I'm just going to put a name for the project here. I'm just going to call it V01 for video 1. And we'll add an executable here. So we're just going to make a project with a single executable that runs natively. So we'll start with add executable. We give the name for the executable. I'm just going to call this main. Note that we don't need to say main.exe or main.elf. CMake sees what platform you're compiling for and will append the appropriate suffix. On Linux, it's not going to append anything, but on Windows, it would append the .exe for us. So then we're going to list the sources that we'll compile with. I'm just going to say main.c. We'll create a main.c soon. But really, this is all we need in order to create a CMake project. So I'm going to create that main.c real quick. Includes std.io. And we will puts hello world. Okay. So, not entirely prepared. Oh my goodness, please. There we go. So if we look at our directory, we have just two files, the CMake lists and the main.c. So another hallmark of CMake is out-of-source builds. The idea that your build files are not in the same source tree as your application sources. If you've worked on large-scale C or C++ projects before, you might be used to seeing a build directory with a debug and a release build, not even a build directory with a blah, blah, blah. Let me start this over. So if we look here at our source tree, we have just these two files. One of the hallmarks of CMake is out-of-source builds. So that's when your build directory does not occupy the same space as your actual sources. If you've worked on a large C or C++ code base before, you may be used to seeing debug and release folders that are adjacent to your sources and all of those subdirectories. This can cause a problem where sometimes maybe generated files are contaminated across different build configurations. CMake opts to sidestep this problem entirely by giving you the option to build all of your sources in a separate directory. So each configuration gets its own separate directory. This can also make your .gitignore very easy to write because you can just say build for your build directory. So I'm going to make a build directory now. I'm going to change directory to the build directory, and I'm going to use the CMake command, CMake, and then I give it a single argument, which is the path to my top level CMake lists.txt. That's just one directory above where we currently are. So I'll let that run, and if I do an ls in here to list what we have here, we can see that it generated a make file for me. CMake will deduce what build system you have available by default and pick that. So if we're on Linux, by default, it'll produce a makefile for you. On Windows, it will probably produce a Visual Studio solution. We'll look at how to customize this behavior a bit later. So now that we have our makefile, we could say make and build directly like that. Instead of invoking the underlying build system directly, I'm going to use a bit more of a modern style. So CMake knows what build system we generated with. As we talked about earlier, it's a build system generator. So in order to keep these steps as generic as possible, I'm going to use the CMake build command, and you give it the directory to the path to the build directory you want to build, and this will invoke the underlying build system for you. So if you're trying to make an automated script that runs CMake for you, this is a bit more reliable of a technique because it doesn't matter if you generate make files or Ninja files or an Eclipse project, this will always work. So I'll go ahead and let that run. And you can see there we go, we built our target main. If I do an ls, you can see that main is right there. I'm going to execute it, and we'll see that we have our hello world. So writing a basic application is that simple. I'm going to go up a directory and delete the build directory here. And I'm going to show you the CMake GUI. On Ubuntu, you can install this with sudo apt-get cmake-qt-gui, qt being spelled qt. When you install CMake on Windows, this is installed for you by default. So this is a GUI application that can do the same thing we just did over here in our other window. So we'll start out, we find where our source is located. I place this in project CMake video v01. You just select a directory that contains the top level CMake lists. So I'll go ahead and open that directory. Then you select a directory that you want the build to exist in. So you can create a build directory, or you can give it a path to a directory that doesn't exist and it will create it for you. So we start out by hitting this configure step. It's asking me if it should build the build directory. I'll say yes. And now I get to select a few more options for how I want to set this up. So by default, it will deduce the build system from your operating system on the command line. But here it lets us choose explicitly, so we can see all the generators that it has available for this platform on Linux. So by default, it's Unix makefiles. Then we can actually change what compilers we're compiling with. We'll talk about this a bit more later, but I'm just going to use default native compilers. This will allow CMake to automatically check what compilers usually exist for that operating system. In this case, Linux, it's going to look for GCC. And I'll let it just find those compilers and use them. So I'll say finish. So you'll notice we have a couple of variables that popped up over here. So CMake exposes a number of variables to the user. We can hit advanced to show a lot more of these. We can also hit grouped, and it'll group them by prefix. In this case, we're not going to worry about that too much. So we say that we have we see CMake build type, and we say CMake install prefix. These are highlighted red because they were changed with the most recent configure. So with CMake, you can reconfigure the project multiple times. So in this case, I'm going to change the CMake build type. This is how you specify if you want your build or release mode. So I'm just going to double click here. I'm going to type in debug. And this will know based on your compiler what flags should be set for debug. So for GCC, it's going to add -G as well as others. And you can configure that behavior, and we'll look at that a bit later. And I'll hit configure again. That'll rerun. I actually double clicked it there. That's why nothing is showing up red. So now we've set all the variables that we care about in our CMake build. And I'm going to hit generate. And that will actually create the make files in the build directory. So I'm going to go back to the terminal and I'm going to cd in there. And we'll see our make file has been generated again. I'll run make real quick instead of the generic version just to show that this also works. You can see we have our main executable again. As you might expect, it does the same thing. It prints hello world. So we just went over a lot of steps there. So let's take a second to step back and explain everything that just happened. So again, we have this configure and this generate button. What exactly are those? There's this really nice website, Seagold. If you just search Seagold in a search engine, it'll almost certainly bring this up. This guy has a great diagram on what happens whenever you run CMake. So CMake has 3 stages that it runs in: the configure stage, generate, and build. So the configure stage, this parses all of your CMake lists files for variables and scans down subdirectories and all that jazz, all the CMake code you write. And it generates a cache. So this contains all of the compilers it finds. It might run some test compiles to auto-deduce what settings your compiler has, and it stores them all in this cache file, so subsequent runs don't need to do all that work again. We can see that we can actually configure multiple times. Let's say we have an option to build tests for our project. We might have it set to off initially, then we might turn it on, and that could, in turn, expose a whole lot more options to us, the user, building the project. So we say, yes, we want to build tests, and that might bring up several other options, like do you want to run the Valgrind tests, maybe? Or do you want to also compile with some sanitizers? So you can see why configuring multiple times might expose more options and might let us, tweak things further. Then there's the generate phase. At this point, generator expressions are executed in multi-config generators. That's all that wording is gibberish right now. We will explain that later. But some generators, like Visual Studio, don't create a separate build directory for each build. Instead, they have different configurations, debug and release, that act. They sort of exist simultaneously in the same build. So generation time controls some of those options, and that gets interesting. The most important part of the generate step, though, is it actually creates your underlying build system. So this is when our make file is created. When we ran the CMake IDE, we had the option to run these 2 steps individually. When we run from the command line, it just runs both automatically. So there isn't a way to just configure or just generate, at least at this time of recording. And it's not terribly useful, in my opinion, to split those steps up anyway. But the subtle differences will become a bit more, it'll become a bit more obvious why they exist later. Certainly, we see that these are portrayed as a linear flow downwards. You can go back and reconfigure. You can go from a generated step and go back to the configure step. You don't have to go to the build step immediately afterwards. So really, all of these can have a loop back if you want to be technical. After the generate step, though, is the build step, and this is when you actually invoke the underlying build system like make, and it creates your binaries. So one of the nice things about CMake is you only really need to run configure once, the configure and generate steps, because what happens on build is CMake checks the timestamps of your CMake lists to see if anything has been modified. And if one of your CMake lists has been modified, it actually automatically goes back, reconfigures, regenerates, and updates your build system automatically. So if I added a new file to my project, it would automatically go back and rerun all of these CMake steps again. So it can be largely transparent to the user after you run that generate step that you're using CMake, which is pretty handy. So I'm going to scroll back up, and we'll see some of that in action. So one last time, I'm going to change directory up, and I'm going to remove the build directory. And when we last ran our GUI, we set the CMake build type to debug. I'm going to do that from the command line this time. So I'm going to make that directory build, change directory build, CMake. Again, you give it the directory of the top level CMake, and then to set CMake options, we use this -d flag, kind of like define if you're used to the GCC command line interface. This is not for the underlying project though. If we say, -d and debug here, this is not going to go to our preprocessor when compiling C and C++ files. We'll look at how to do that a little bit later. This is for CMake itself, the actual build system. Also note these are not environment variables. A lot of CMake options like default compile flags can be set through environment variables, but generally you want to set them through the command line. So here I'm going to set the CMake build type, say equals debug. I will go to we're already in our build directory. So I will run make again, and there's main. And just to prove that this puts debug symbols in here, I'll just run gdb really quickly. I will be at main. Let's enable the text user interface. Give it a run. Here we are. We're at main, so we can, in fact, debug. And we'll just run to completion. So it really is as simple as that. So now that we have our build directory, I'm actually going to go back to our CMake lists. And what we're going to do is we're going to add another source file. So I'm going to create a hello.c. And over here, stdio.h, I'm going to move that hello world into this file. So I'll just make this a void hello. Okay, over here, I'm going to add that hello.c. And then I'm going to go back to main.c. I'm just going to type the prototype manually. And then let's rebuild this. So note, I'm not going to run any CMake commands again. I could do CMake --build dot. That just delegates to the underlying build system. But to prove to you that I don't need CMake to update this, I will run that again. You can see here it compiled our hello.c object. And if I run main again, we get hello world. Let me change that to something a bit different, just to really hammer it home that this indeed works and I'm not lying. Hello world from other file. And you'll see, hey, look at that. It didn't recompile main. It only relinked main because it didn't need to recompile main. So we have all the dependencies set up properly for us automatically. So I'll run main again. We see hello world from other file. So again, that was to demonstrate this back loop in our activity diagram here. It checked to see if the CMake lists changed, and it did because we added that extra .c file to our compile step. So it went back and reconfigured and regenerated and went back to build. So CMake having these sorts of compiler abstractions is really, really powerful for us. So we've done something really, really simple to start. Most projects aren't going to be a single directory with just a couple of files. So let's take this opportunity to add another directory with a few more files. So I'm going to remove the build directory. You can see we have just our few files right here. And I'm going to create a couple of libraries, and I'll make them kind of things that you might see in a typical project. So I'm just going to make directories for all these. I'm going to make a directory for a logger. I'll make a directory for a sensor. I'll make a directory for a UART driver. And we're just going to do fake versions of all of these just to see how everything works. So let's remove hello.c from our project. So let's start by just making a CMake library out of logger, and then we'll add the rest of these together. So I'm going to start by making another CMake lists file. You don't need to make a CMake list per directory. If you share code between projects, though, directly just source inclusion. This can be really a really helpful way to structure these kind of things, because you could put logger in a submodule, for example, and then add this whole library with just a single CMake command, and we'll see that soon. So let's start by just editing another CMake lists.txt. So just like we had add executable, we're going to add library, and I'm going to call this library logger. Now, you can specify what kind of library you want to create. We'll go over this more in detail later. CMake defaults to static libraries generally. We could say static here explicitly. We could also say shared here explicitly to make it a shared library. I'm going to leave this blank because there is a project-wide default setting that, again, CMake opts for static by default. But if our user turns on shared libraries, we don't want to override them without just cause. So I'm going to leave this blank and let CMake automatically deduce that this is going to be a static library. So add library looks very similar to add executable. You just list the sources that are part of the library. So I'm going to create a logger.c. I'm also going to create a logger.h. Now, there's a decent question to be made here. Do I need to explicitly list header files? I would argue that it's good practice to, at least. As we see later when we generate IDE projects, some IDEs don't automatically pick up headers that are used in your library. If you explicitly list them, almost every IDE certainly will. It also makes your build a little bit more resilient. This way, if the logger.h file gets deleted, CMake will fail at configure time and say, I couldn't find logger.h where you were saying logger.h should exist. Dependencies will resolve properly without listing headers under all the generators that I am familiar with. But for the sake of being paranoid, I think it's also good to list every file explicitly just to make it really clear. If this file changes, the target should change too. Now again, header dependencies and include dependencies do propagate properly with CMake when it generates make files or ninja files, etc. The MD flags, I don't remember them all exactly, but those flags CMake adds correctly, so you don't need to worry about managing all of that manually. And really, this is all we need to do to add a library. So I'm going to go ahead and write that. And let's do a split here. And I'm going to add this logger.h and logger.c real quick. So this is going to just be a really dead simple logger, maybe not even really a logger. So I'm going to create a function. Oh, function log. Actually, log's a reserved name. There we go, capital L log. Give it a const char star message. Okay, and then I'll create logger.c. Going to paste that same function prototype. Apologies if I'm inconsistent with my spacing in new lines. And I'm just going to make this print f. Okay. %s message. Okay. Let's go back up to here. So we've created our logger. I've gone back to our top level CMake lists, and I'm simply going to say add subdirectory logger. So here, all I'm doing is I'm saying CMake, look in this directory called logger and see if it has a CMake lists.txt and execute that. If our logger subdirectory didn't have a CMake lists.txt, this step would fail at configure time. So we could take all of the code that is in this logger slash CMake lists.txt, and we could move it over to our top level CMake lists. Of course, we'd have to add the logger directory in front like that. That's also fine. Some projects opt to have just one big build file just so it's all in one place. For these tutorials, I'm generally going to split things into subdirectories just because it makes each individual chunk easier to understand and use. So we've now added our library to our project. Our library will be built. I'm going to now we have to link against this. I'm going to say target link libraries main private and then logger. Okay, so I'll explain what all of this means soon. I'm going to go back to our root, and I'm going to make a build directory. I'm going to change directory to build. I'm going to run CMake real quick, and I'm going to build okay. Now, I didn't update the files. Let's go back to main.c. This function no longer exists. So I'm just going to include logger, logger.h, and I'm going to build that again. I will, well, running main is not going to do us much good because I haven't actually used logger yet. So linking is that simple. We now can actually use our logger. Let's actually use it. Log hello. There we are. So let's give that another run. Give it a build, give it a run. You can see we printed hello. I messed up something. I didn't put a new line afterwards, I guess, so my shell's complaining. That's all well and good. So let's take a look back over here. We added our logger. We probably don't want to specify these paths for every library we use, though, especially if paths are, up a directory. So let's see how we can actually use include directories properly. So I'm going to give this a up. Let's give that a right and a close. Okay. I'm going to open the logger CMake lists file again. So let me explain some of what's going on here. So anytime we add a library or add an executable, it creates what's called a target. So targets are just like makefile targets. They're sort of the output of a build. We will see phony targets later, that is, targets that don't actually output anything. But the important thing to know here is that we can link targets together to say that one target depends on another target. That's what we did over here with target link libraries. So the main target depends on the logger target. And we can also attach properties to targets. So I can say target include directories. I'll say logger, that's the target that I'm affecting. I'll say public, and I'll just give it a dot for the current directory. So what have I done here? I have said that in order to compile logger, you need to add the current directory as an include directory. And to link against logger, you also need to include the current directory as a include directory. In GCC, this would be the -I flag, capital I. So if we go back to our other file, we have private here. What this says is that main requires logger and all of its associated properties to build. Now main's an executable, but if main was a library and somebody linked against it, private says do not propagate the properties of logger to whoever links against me. This public says do propagate the properties of the logger target to whoever links logger. So this is known as transitivity control. This is the transitivity of properties. So we'll look at this a little bit more soon, but we'll see that this include directory for logger is going to be propagated to main as well. And that's public that lets us do that. If we said this was private, we would not be able to see those include directories. So let's actually see this in action. Let's edit our main.c, and we'll just include logger.h. We will run CMake build, and I will give it the build directory. Then I will run build main. There we go. You can see that it's still built and linked and ran successfully, which is good. I'm going to go back and edit the CMake lists, and I'm going to change this to private. So what this is saying is, in order to build logger, logger needs the include directory of the current directory, but if you link against logger, we do not want this include directory to propagate out. We want to keep this property private to logger. And this is going to cause an issue. We'll see no such file or directory, logger.h. It cannot find logger.h because that property was not propagated. So you can imagine properties aren't just include directories. Properties can be other link libraries. Properties can be compile definitions. Properties can be compile flags even. So a really useful common example of using these private properties is, let's say we have a third-party library that we trust. We might want to disable warnings in that third-party library because it knows a number of things about the platform we don't know maybe. A board support package, perhaps, might do some things that aren't strictly speaking portable, but we know are safe for our board. So we might want to disable warnings for that particular library, but we don't want to disable warnings for the entire project. We could set a build property, a compile command property on that target to disable some warnings and make it private so that when we link against that library, we don't also disable the warnings for everything else. So this sort of control over the transitivity of properties makes CMake projects really powerful and really concise. So we made a very basic logger. Let's actually, oops. Here we go. Let's actually add a new line to this. Okay. Up. And we will go back and fix our CMake lists. So I'm going back to the logger CMake lists, changing this back to public. Note that we use private for main. This doesn't really matter what it is since it's an executable, but it's good practice to set these transitivity properties explicitly. Okay, so let's build that again, and I will run that again. Okay, yep. We're back to a properly building state. Okay, now I'm going to add some basic fake UART and fake sensor functionality. So I'm going to speed this part up slightly. This code will all be available publicly on GitHub, which I will also link in the video description. So let's start with UART. Okay, so I filled out these other modules over here, sensor and UART. Let's take a look at the additions. I also fixed idiosyncrasy with logger. So logger.c now includes logger.h. Sensor is a fake temperature sensor. So in sensor.h, we include UART, and we say sensor read temperature from this given UART. If we take a look at sensor.c and how it uses that UART, so sensor, we're pretending that our temperature is just a regular natively sized, natively endian int for convenience. We do a UART read, given the UART instance the user passed in, and we use our logger to say that we are reading a temperature, and we simply return that temperature that we read from the UART, assuming our UART protocol is just sending temperatures, and this is a greatly simplified example. Okay, and then UART, UART H. We're pretending that UART is a struct that you might see in a HAL. Right now, we're just treating it as an int. In reality, we have a UART init and a UART read. All that UART read takes is the UART instance, a void star for output, and a size and number of bytes. And then our actual UART implementation, quote unquote, is just using random numbers to fill out the buffer. So in our UART init, we don't actually set self to anything meaningful. We're just using rand. We're just seeding the random number generator. Then we're just looping over the size of the buffer that the user provided and writing random bytes. That should be, there should be some casts here, but again, this is all greatly simplified. So we've written our drivers. We have not done any significant edits to the CMake lists. So currently the CMake lists all look basically identical. The only differences being the library names and the files listed. So currently this build is going to fail because we haven't actually linked against anything yet. Oh, lastly, how do we use this code in main.c? So our final objective here is for main.c to be able to include sensor. Sensor will transitively include uart.h, and we will initialize our uart. We will call our sensor read temperature. This should call the logger message, read the random bytes, and print out the temperature that we have read. So this is how we want our usage of our code to look like. So how can we get there? I want to note again, before we start, that sensor, sensor.h, this includes UART.h, so it can have access to the definition of UART. Technically, we could just forward declare a UART here, but regardless, we are including UART.h in sensor, so we're going to need this publicly. But in sensor.c, we include logger only in the implementation, so we're going to link this privately. Oops, there we go. Okay, so let's start by just including our other modules. So I'm going to include sensor, and I'm going to include UART. So just like that. Then main isn't going to link against logger, it's just going to link against sensor. And then we expect that main should be able to get all of the transitive dependencies it needs for UART out of sensor. That's our goal, is to make all that linking up automatic. So now, let's make that happen. Again, we're going to go into UART's CMake lists. Oh, actually, apologies, UART is already done. We're going to go into sensors CMake lists. So currently, sensor doesn't even know where the UART header lives. So we're going to fix that right now. We're going to target link libraries for sensor. So we want our UART include directories to be propagated transitively to those who link against us. That is to say, sensor needs UART.h both to build itself as a library, and those that link against sensor are going to need that same header so they can actually instantiate a UART. So that dependency is both for sensor internally and those that use sensor. So we're going to list that as a public requirement. So here we will list UART as public. Now, logger is the exact opposite. Sensor needs it to build, but those that use sensor don't need to know anything about logger. Logger is purely an implementation detail of sensor, and we want to keep it that way. So this is how we hook all of that up. So now, let's make our build directory. Let's do our CMake configure. Oops, I forgot to change directory to build. Let's run our CMake configure and generate. And we will run our build. Oh, unknown type UART. I have made a mistake. Let's go to UART, UART.h. Oops. There we go. I am confusing the using alias syntax in C++ with the type def syntax. Oops. Okay. Whoops, conflicting types for UART read. Okay. Let's see. Implicit declaration of UART read. Okay. Let's take a look at that. Oh, unknown type size t as well. Let me go to UART, UART.h. Okay, there we go. Oh, implicit declaration of built-in function printf. That is in main.c. Let's fix that as well. Okay, there we go. You can see we can run this a bunch of times, get some random numbers that are not particularly random. Either way, our linking propagated all of our dependencies properly. Now let's actually double check to make sure that's the case. So I'm going to go back and edit main.c, and I'm going to try and include logger.h. I should not have access to this because, again, we don't link to it if we look at our CMake lists on the left-hand side here. We only link against sensor. And again, logger was a private implementation detail of sensor. So this actually should fail to build. And it does because it doesn't know where logger.h lives because we did not propagate that dependency. So I want to show you a couple of extra neat CMake features you can use to diagnose these sorts of things. So the first thing I want to show you is a variable. We'll get to this syntax a bit later, but CMake export compile commands on. Going to run another build. Whoops. Well, this is actually fine. So that failed. Whenever we set CMake export compile commands on, it generates this compile commands.json file for us. This is just a convenient way to look at all the flags that CMake uses to build. This is not a particularly convenient view. I will close these out. There we go. List the file, the directory, and the command. So you can see it's actually using CC, which is just an environment. It uses our C compiler from our environment. You can see that we have an include directory of sensor for main.c. We have an include directory of UART, and the rest is just compiling. For logger, we have an include directory of logger, and that's it. For sensor, we have an include directory of sensor, we have an include directory for UART, we have an include directory for logger. And lastly, for UART, we only have an include directory for UART. So you'll notice for main, again, only the public sensor properties of include directories were propagated to us. So again, only sensor and UART include directories, not logger include directories. Those are private to sensor. So let's go back and fix that up. Oops. Make sure we can build. And we are still in business. So the last thing I want to show you is a lesser known CMake command. So you can say CMake, I believe it's graph viz equals, and you give it a name. I'll call it TGT graph or target graph, and the directory of your top level CMake lists. And it creates all of these graph viz files. So if I do an ls here, you can see we have TGT graph, logger depends, etc., etc. So if you use a visualization tool like xdot and you look at the TGT graph, it'll actually show you a dependency graph of all of your targets. So we'll see that main, it's this little house shape. That means it's an executable. Links against sensor. Sensor is a diamond shape. That indicates that it's a library, which links against both logger and UART. You might also notice that we have dotted lines and solid lines. The solid lines indicate a public dependency, a public transitivity for linking, and the dotted lines indicate a private transitivity for linking. So we see that sensor privately links logger, which is why main can't have access to it, but it publicly links UART, which is why main does have access to it. So this is enough, I think, to get you started with some very basic CMake projects. This is sort of the general idea for the out-of-source builds. We set our debug flags as well using the CMake build type. We created all of these targets with different transitivity of our dependencies and put them in subdirectories. And at the end of the day, we don't really have much build system code to show for it, which again is one of the nice things about CMake. This is not a very big project at all. This is all relatively easy to understand once you have the basic mechanics down. So that's all we're going to cover for right now. Hopefully this is enough to get you started.